forgot to start the recording again. I log on and I stop the recording and then I forget to turn it back on. So sorry, Eli. You'll have to learn about asymptotic series on your own. It's in the notes. So let me see. The point here is this integral diverges logarithmically. Okay, this correction, if we, oh, there comes Alex. All right, what are we, yeah. Welcome, Alex. Hey, you made it, good. So this integral, if we integrate the, let's see, squared. We integrate this over that internal momentum, which is completely undetermined. So we add up all possible internal momenta here, except that this has, this turns out to be an integral. Okay, we have d4k, then here we have a k squared that comes into it because we square that propagator. There's a t minus m squared. Then various factors that depend on various dot products. And let me think, is this, yeah, I'll just write it down. There's 64 m squared t. Then minus 128 m squared. PT is going to be this difference here, p minus k. And then 64 m squared. So working through that matrix element, this squaring it, taking the traces, doing the usual things here. This is what I ended up with. I've only done it once, so I don't promise it's right, but it's sort of right. So now we take the center of mass frame, so that this p alpha can be just m and 0, and the what else? K alpha is in some direction. So this k alpha here we can take to be some magnitude. Let's call it the frequency omega times the null vector. So any unit vector you like here. Then we have t in this basis turns out to be m squared minus twice the dot product of m and omega, a dot product of these two times 2, plus k squared, but k squared is 0. So just squaring out that difference. And then p dot pt is then omega. So this p dot pt turns out to be just m omega. So we have all the dot products from here. We can substitute all those in. And yeah, it's not too complicated a thing. This integral turns out to be, let me write it down here. So that was the matrix element. So d4k m squared ends up being, I think we end up with an e to the m, 40 squared over m squared. And let's see, yeah, okay, d4k over, and here's the key thing is we get 4m squared omega to the 6th. Where that 4m squared is suspect, that's probably not there with the proper normalization. and then a polynomial starting with that omega squared, m squared, omega squared, here, minus 8 m cubed omega, plus some 4m to the fourth. There we go. Okay, so we do that problem, we square the matrix element, we substitute in to see what this contributes, and the key is this omega to the sixth. D4k is a D3 over angles and a k cubed, or omega cubed d omega. And so we have omega squared is the highest term here, omega cubed in the volume element, omega 6 in the denominator. So we end up with the omega over omega, which diverges logarithmically. So we have a divergence here. Now, the simplest way to handle divergences, and something that works for QED, you need something more sophisticated for a non-abelian gauge theory, and I'm hoping that we get to that. But you put a cutoff, right? You put a highest value of omega, and then you go through the calculation, and you renormalize. So what happens here is that this this possible divergence, and you can have as many of these as you like. We've actually seen a case like this before with the scalar field, where we summed the whole thing. We found we had some divergence I delta, and that the propagator, the full propagator for a scalar field was the bare propagator plus terms like I delta sandwiched plus two of those things. So each time you added one of these loops, you added that divergent thing like this. So you get something like that. The same thing is going to happen here with this electron line. And we were able to sum this and show that it ends up being, for the scalar field, p slash minus quantity m plus delta, or let's see, no, not p, this was scalar field, p squared minus m squared plus delta. And you get more systematic about this. You find that at fourth order, there's a new infinity. But we have constants, measured constants in QED, the charge and the mass. And what happens is a propagator, by the time you do this kind of resumming of the loop diagrams, the propagators end up being something like, Z1 P slash minus Z2 M plus Z3, something along these lines, where you have three distinct divergent integrals. And what you do is you choose those so that, let's not worry about this one right now, so that this is the measured value of the electron mass. So you have these corrections, at each order, and as you increase the magnitude of the cutoff, these change. But what you know is that by the time you include everything, the result should involve the actual measured electron mass. So we talk about the bare mass, the one that you start with in here, and then the dressed mass, or the physical mass, as the one that we set all of that equal to. Now, these numbers may or may not diverge, but it doesn't matter. Once you've done this replacement with the electric charge and the electron mass, you've fixed all of the divergences, right? It turns out that at higher order in QED diagrams, the thing you see you'll have fairly complicated diagrams possible, right? So, this will be some kind of scattering thing, and these may exchange a photon and those, and so on. But what happens is that the only loops you get are along propagators like this. They're iterations of this same divergence. So you can break the diagrams up, and each piece of it gets this replacement, and all of the things that diverge are gone. You only ever have this finite number, in this case 2 or 3, of divergent integrals. And by renormalizing those, you get rid of all of the divergences that you get with any diagram. So you've completely, renormalized is the word. There is a whole theory of this stuff. One thing you can imagine is putting using a box normalization like we did for the cross section. If the problem is in a box, there is a momentum cutoff. And one thing that renormalization group theory does is say, okay, if I double the size of the box, so the volume goes up by 8, the space-time volume goes up by 16, what happens to each constant? And each constant will pick up, 2 to some power, probably, but changes in some definite way, such that if you rescale everything by that factor, you're looking at the same problem on the bigger box or the finer resolution box, whichever way you choose to go. And people talk about what's the term for, basically the idea of significant and insignificant variables that grow when you do that, variables that shrink. Any variable that shrinks when you increase the resolution of the box, the fineness of your description, irrelevant is the term. So irrelevant variables simply go out of the calculation altogether as you scale up. The relevant variables are the things that grow, and you have to renormalize. So a renormalizable theory is one where you only have a finite number of these kinds of divergent diagrams, and everything else can be expressed in terms of them, and you put in the measured values for those finite numbers, and now you have a fully predictive theory. A non-renormalizable theory introduces new divergences at each order in perturbation theory. They're not useless, but you don't want to carry that approximation to arbitrary orders, because you're going to have an infinite number of things you have to measure before you know what the theory is predicting. You can still get some interesting results out of a non-normalizable theory. It's not, the death of your perturbation to have that. It has stricter limitations than a renormalizable theory. The thinking sometimes has been that an ultimate theory ought to be renormalizable. Gauge theories are renormalizable. So we're on safe ground with the standard model. Now, yes.
Are there set criteria for renormalization? Do you just have to calculate it and then find that it's what the series looks like, or is there?
There's a very easy way to tell if it's probably renormalizable, and it's called power counting. So the procedure, I'm going to have to read my notes to get this right. Basically, you can estimate for diagrams like this, or any diagram, you can estimate the degree of divergence that you expect to see, because each vertex, let's see, each loop is going to, here, let me write this down. You're going to integrate over each loop. of each unknown momentum, each momentum that is not determined by your boundary conditions. So, so you have the number of loops and if D is the dimension, and I mean the dimension of space-time, so we're probably dealing with 4. Let's just call that 4 for now, but of course people do this in various dimensions. So you're going to have 4n times integral d4k. All right, that goes as 1 over length to the 4th. Each momentum is an inverse length. All right, then you have propagators. And you have to look at various sorts of propagator, and you also need to look at different sorts of interaction. Okay, here you can write the number of loops in terms of the number of vertices, but that depends on the interaction. So here a vertex introduces, it changes one line into 2, and that implies a certain number of loops if you have a certain number of vertices and boundary terms, boundary particles. So depending on the particular
Professor?
theory. Yeah.
Is it something fractal? Is it something fractal? It's some type of fractal exponent or something?
No, it's much simpler. It's just, let's see, it's going to be this 4n, but then we subtract the number of propagators. So we have 1 over k squared for a photon. For a fermion, we're going to have 1 over p slash minus m, but that's p slash plus m over p squared plus m squared. Is that right? P squared minus m squared. Which, if we look at the worst divergence here, that's going as 1 over a p squared. Or a scalar field, we know it's p squared minus m squared. So again, that's going to diverge like p squared at large p. So basically, all of these introduce a length squared. So if the number of let's see, what do I call it here? L, yeah, the number of internal lines. All right, so what we need to determine the degree of divergence of this is we look at 4n minus 2l. So 4 times the number of loops minus 2 times the number of internal lines. And basically, the integral is going to be something like p to the 4n minus 2l. Well, if this number 4n minus 2l equals 0, that gives a logarithmic divergence. Okay, that's basically d omega over omega, right? That's what happens if that number is 0. If that number is greater than 0, then what do we have? We've got let's see, which way does it diverge? What did I say here? If it's yeah, it diverges if this is greater than 0. Greater than 0 implies that it diverges. And so if this number is bigger than 0, it's probably non-renormalizable. If that number is less than 0, it's renormalizable. Different theories with different numbers of vertices, per line. If you express this in terms of the number of vertices, that will vary. So there are various modifications and proofs, but this is the basic result for QED. You can, as long as that is negative, you're good. 4n minus 2l equals 0, and it's logarithmically divergent, but you can handle a finite number of those. It's not, this is not a complete proof because there could be funny cancellations and things that make something divergent even though it looks superficially convergent. But this is a fairly reliable guideline. Okay. Yeah, that's.
Yeah, sorry, is it like a loose, is that like a loose measure of like surface area to like vertex density or something like L is like a measure of like the number of like points originating from a vertex, and L is like the density of loops in the total phase space. So is this some like fixing criteria where you have enough points at every vertex to locally orient or something? Yeah, I'm just trying to get what the criteria we're measuring are. Sorry.
Yeah. Okay. All right. All this is looking at is the order of integration you expect to get from the matrix element. All right. When you integrate the matrix element over all internal free momenta, this is the naive divergence that you should see. Now, whether that corresponds to orientation of some surface, you know, I mean, you might look at that in string theory and ask what happens there. But yeah, I haven't seen a deeper discussion of, you know, what that particular number might be counting in some physical sense. It's just the naive divergence of the integral. Let's see. So now, virtual particles and resonances. I want to talk about this a little bit. Let's see how we're doing. Oh, we're good. So you guys know the optical theorem? All right, probably worth it. You know, it's a very general theorem. In fact, Heisenberg did a more general version of it than this, but it's a fairly simple result to get to. So let's have at it. Yeah, I'm gonna have at it with a fresh marker here. So the result, the statement of the optical theorem is that the cross section for scattering is related to the imaginary part of the scattering amplitude. So we can write the sigma as 4 pi times the imaginary part of f of 0 over the momentum, I believe. Yeah, that's right. But now let me tell you what f is. If you do a scattering experiment, say just classically, but a very similar thing holds relativistically, you can write the wave function as an incoming plane wave. Let's have it come in the z direction, plus a scattered wave with an amplitude that depends on theta on the direction of scatter. Could depend on phi too in principle, but let's stick with a simple case here. And then an outgoing radial wave where we're interested in the 1 over r part. That's the radiation part. You know, there, when you do an expansion in spherical harmonics of like the outgoing wave of a scattering experiment, you find inverse powers of r with the various spherical harmonics. But in the limit of large distances, it's really only the 1 over r part that is your normal radiation field that you see at infinity or at a great distance. So we look at that part. So we're going to drop terms in 1 over r. And the other thing we imagine is, okay, we've got this plane wave coming in. You know, it hits some scattering center, and you get a small angle scattering. So, you know, what you see is some fairly narrowish peak off here at some great distance. So we're going to take z much greater than the other coordinates. So r can be written as x squared plus y squared plus z squared. But I can pull out a z and write that as 1 plus x squared plus y squared over z squared, and do a Taylor series of that. And I have z plus, then I get a half of this and one z cancels. So x squared plus y squared over z. And if I put that into my scattered wave, this becomes e to the I k. Actually, I can pull out a factor of e to the I k z. Then we have f of theta, and e to the I k r becomes e to the I k z, which I pulled out, plus e to the I k. Then we have x squared plus y squared over z here. And then this is over, and now we call it z plus small correction. So r is about equal to z plus x squared plus y squared over z, yeah. And we can think like this. So now we're just going to make some radical approximations here, and it works. It actually gives us a very general result. So now the thing to notice about this remainder is that this has the form of a Gaussian. So if we now integrate over the area of the screen, so we're going to okay, so we've got some fairly small peak. You know, if it's an interference, the criterion is basically you need to include several fringes of the interference pattern in order for the approximation to be valid. But what happens is this dies off so fast that we can extend the integral to all of x and y. So we're going to integrate dx, dy all the way from minus infinity to infinity, and incur very little error outside the small error area of the screen. So what we're interested in is basically psi star psi. Now we've got a probability density that goes like psi squared, and then that is going to be, well, let me see how to write this. Yeah, it's yeah, we're going to integrate this. There's some normalization which we don't need to worry about, but the e to the I k squared goes away. We have an integral over x and y of this magnitude squared, 1 plus, what did we end up with here? F of theta over z e to the I k squared plus y squared over z squared. And since we're ignoring the 1 over z squared parts, we just get the cross terms. So this is going to be, I'm going to change this to polar coordinates. So I'm going to have a rho d rho d phi here instead of dx dy. And then this is going to be 1 plus the real part of f of theta over z e to the I k. Then this just becomes rho squared over z here. Let's see. Yeah, that's the cross term. Then the quadratic term drops out.
Is it 2 times? Is it 2 times the real?
Yep. Thank you. Twice the real part. Yeah, I'm doing 2 steps at once here. Sorry. So we want to do that integral, but that's just a Gaussian integral. And the other thing we do is we approximate, you know, since this is small angle scattering here, we're going to replace f of theta by just whatever its value is at the origin. So then we bring the integral inside. This first term just gives the area. The area, there could be some normalizing factor here, but this gives the area of the screen, which doesn't have to be infinite. We can still carry these integrals to infinity because there's nothing out there because of the Gaussian drop-off. But the integral we need, we're going to want 2 real part of f of 0 over z times the integral. We do the phi integral, that's 2 pi. And then we have the integral 0 to infinity of rho d rho. Sorry here. Let's see. Got that down here. E to the I k over z rho squared. So this brings us right to the trick to evaluate a Gaussian. So we only need one other trick because the one's implemented already. We're gonna write this integral rho d rho e to the I k over z rho squared. Let me be sure I lost a half. Oh, the Taylor series, there's a 2 here. The Taylor series of the square root had a half. Okay, so then rho squared. This is right, but I'm going to put let's see, do I even need to do it? Oh, yeah, probably do need the trick. Right, I'm going to write this as the limit as epsilon goes to 0, and I'm going to add an I epsilon convergence here. But let me see where I add it. Yeah, I put a 1 plus I epsilon here. So the I squared gives a minus a negative exponent that will give me convergence at infinity. And then I take the limit as epsilon goes to 0. So this is all equal to, if I let psi equal rho squared, then this is the limit of 1/2 the integral of the psi, that would be twice rho d rho, and I cancel the 2. Then here, the exponential of I k over 2z 1 plus I epsilon psi. And then I just integrate that. So I have the limit 1/2. Then I have 1 over the coefficient I k over 2z 1 plus I epsilon times the exponential psi as psi runs from 0 to infinity. And all right, at infinity, I've got minus epsilon psi goes to 0. So the convergence factor I put in gives me 0 at infinity. So I only evaluate this 0, and at psi equals 0, the exponential is 1. So I'm simply going to end up with z over I k with the 1 plus I epsilon, but I take the limit, and it just is z over I k. So turns out to be a very simple integral. And now the thing that we're computing is the total area of our screen. And then what do we have? We have the real part of 4 pi f at 0 over z times z over I k. the z goes out, and the I becomes a, minus, subtracted the lower limit, so there's a minus sign here somewhere, minus. Okay, so minus 1 over I becomes I, and the real part of I times something is minus the imaginary part. So this is just A minus the imaginary part of 4 pi f of 0 over k. And that gives us the theorem, because what we're seeing here is the probability of psi being the area minus some scattered fraction. Okay, so what this is telling us is that this imaginary part is the probability that the wave scattered and has not gone straight on through, but that's exactly the total differential, the total cross section. And so we equate the cross section to 4 pi times the imaginary part of this ratio. Okay, that's the optical theorem. You know, cool thing, really useful in optics. If you've had an optics course, you'll have seen that. Now,
Professor,
yes.
that almost says that almost sounds like it says something strong about interactions and waves, like some type of some type of picture is always valid. Is this like confirming like the Heisenberg picture we took in the interaction scheme is valid? Or yeah, what is the sorry.
Okay, yeah, all right. My main motivation in giving this is to point out that it's really the imaginary part of that scattering amplitude that's going to produce your cross section. The same thing is true for these scattering problems, right? The term we get is the exponential of the I over h bar times the Hamiltonian, which is a unitary operator. And we've made it unitary because that preserves probabilities. That doesn't allow for a particle to decay. If we want a particle to decay, we're going to have to add an imaginary part to the Hamiltonian. And the optical theorem, so perhaps a more general version of the optical theorem, there is one due to Heisenberg, in fact, will tell us, you know, suitably manipulated for the relativistic case, will tell us that an imaginary part in the Hamiltonian is going to lead to particle decay, you know, a change of probability. And that's the only way we're going to do it. You know, e to the I h, the Hamiltonian, is a unitary operator. So an imaginary part there, say an I gamma, is going to give an e to the minus gamma, and that's going to decrease the amplitude. It'll decrease the value of psi squared, and so allow for the fact that that particle has decayed. Now,
is this a limit where you can Wick rotate into thermodynamics?
That's the Wick rotation. I think we discussed that, I don't know, a couple of weeks back. We talked about the Wick rotation. When we do these divergent integrals, right, the one I just got, the d omega over omega, what we do to do those integrals is a rotation in the complex omega plane so that it actually becomes a Euclidean integral. And that also establishes the connection between this quantum field theory and condensed matter, right? Because basically the Feynman path integral is a Wiener path integral where you've replaced the temperature by an imaginary time, right? The Wick rotation, you take t to it. We showed how that dodges the poles, and so that's a legal rotation as long as you go counterclockwise. And basically, once you do that, now you're doing a Euclidean path integral, and that's that can give you the Fokker-Planck equation, You know, that comes up in condensed matter all the time. It's amazing the number of PhDs in particle physics who end up doing condensed matter. You know, it's you get to do some of the same math, but apply path integral techniques to statistical systems. So yes, absolutely, Alex. You know, there is this equivalence between these things. Ooh, we lost Kevin. Hope he didn't have to go. Okay, let's pretty much jump to the propagator here. If we add an I gamma term to the Hamiltonian, that's going to change the propagator, and we're going to be looking at something like, is that my good marker? The propagator is going to become something like this. I should look at which way I want to do this.
And sorry, just to follow up on that. So in all of these equations then, in the statistical, like the Wick rotation, do all these become heat kernels then? All the propagators become heat kernels?
Yeah,
for different,
exactly. Yeah, we're looking at, yeah, the green function is a heat kernel, right? All of these things, yes, are the same for sure. So just want to look at which way to do this. Yeah, let me run through it this way. So essentially what happens is that the one way you can treat this, that's not my new marker, let's see, must be this one. The mass becomes, takes on a real plus an imaginary part. And I'm going to call this minus I gamma over 2, because that makes the numbers work out right. Ultimately, that's going to make gamma into the full width at half maximum of a distribution. So putting the 2 there is a nice thing. In our propagator, so a propagator is going to have, okay, a coupling constant. It's going to have a p squared. This is a scalar field minus the mass squared. So we get mr squared. And the cross term here, we're going to neglect the gamma squared. We assume that this decay is a small contribution. So we're going to get a plus IMR gamma, like this. And so that
can I ask another silly question? Is like the imaginary mass something like the particle number inertia or something, like what or interaction inertia or
particle number inertia? Okay, could be. It could be. All right. Remember, I said an imaginary part to the Hamiltonian. So if you think in terms of an interaction, so take some free particle, you know, a bunch of scalar fields, say, some action, and add some interaction between those fields. All right, now do your loop corrections to the mass. If those ever come out, well, there's an I in the Hamiltonian. So if those guys ever come out real, you get an imaginary part to your propagator. So you can produce a thing like this from loop corrections from an interaction term. So basically, write any interaction term for your fields. So, you know, you're thinking of a Higgs field probably that is responsible for a constant interaction that leads to inertia, right? Yeah, so you could do that. I'm not sure that's going to give this decay, right? What you're looking for is an imaginary piece in the propagator here. Because when you look at m squared, that's going to go like g squared over, you know, you have your s minus mr squared plus the imaginary part squared, like this. And that is a resonance peak. Okay, if you plot that right near, right, so if you're varying S and this is MR, then when S is equal to MR, right, this is staying the same. So this has its maximum when S equals MR, and so you see a peak like this. And if you're combining this with the rest of your scattering amplitude, there could be all kinds of stuff. Often you'll see experiments where you've got some decay thing happening, and then there's a little blip here. It's a resonance peak, and what it signifies is that there is some actual particle with that mass, and you've passed over that point. It's decayed quickly, so you may not have seen the particle itself before it decayed, but you see the finiteness of this resonance. If you didn't have that imaginary part to the mass, you wouldn't have this term, and this would diverge for some values of S. Now, S in the center of mass frame is like it's like twice the energy or something, or that squared, twice the energy squared, I think, something like that. So each particle coming in has the square root of 2e, but if there's actually a particle with that mass, you've made it, it's decayed, but you still see it from the resonance peak. So this is a very frequently used tool in scattering experiments to detect rapidly decaying products. You get enough energy and you see that resonance peak, even though the particle has decayed back into the things that produced it. Perhaps you could have, if you had a term, phi 1, phi 2, phi, say, you had an interaction term like that in your Hamiltonian, then you could have a diagram where phi 1 and phi 2 come together, briefly form a phi, and it goes back to a phi 1 and a phi 2. So second order thing, but you could detect the presence of that phi particle by its resonance peak.
And then so then is gamma is some like measure of the particles like propensity to free propagate versus interact, like a measure of its interaction.
Yeah, so
like,
if you have a pure resonance peak, gamma is the full width at half max. If you're familiar with the statistics, you go half the height and you measure the width. It's not quite the standard deviation, but it's a perfectly good measure of the spread of a distribution. So gamma, with this normalization, that factor of 2, in fact, is the full width half max.
Is it the temperature then?
Well, here it's an energy, so temperature, yeah, sure. If Boltzmann's constant is 1. But yeah, that's the idea. Okay, so let's see, how are we doing? Hour and a half, how are you guys holding up? What was that? You good?
I'm alive.
I missed the gesture there.
I'd like to cut it here. I'm getting tired.
That was scissors. Okay, I couldn't tell if it was like a shaka or a finger or okay, scissors. Got it. Yeah, we could stop here. We could all work Miller scattering together if you like, but I think that's one you can do on your own. And so, well, I'm not sure what I'll get to next time, but anyway. Yeah, this is a good spot to.
I had one question actually about the photon scattering. How do you go about setting up the matrix element for that?
Oh,
because you get like the box of fermions in the middle, and And to conserve lepton number, you got to have like positrons and electrons in there. So how do you go about following the time there? That's what I was asking.
No idea. Let's try it.
Okay.
Let's try it. Yeah, that just seemed like a cool thing to at least take a start at. But we know the diagram and we more or less know the rules. So let's see if we can follow it. So we've got photons, 2 photons in, 2 photons out. Oh, I know what I was gonna compute for you. Yeah, all right. Yeah, this is what the next hour would be before I do this. But it's in the notes, so you can read it and it's just a calculation. Okay, when you compute the differential cross-section or the decay rate, you integrate over all the final momentum. And that's like, you know, D3P, D3K for Compton scattering, something like that. You've got 6 momentum integrals. Well, you have that conservation of energy, conservation of 4 momentum delta function. So you've got 6 integrals and 4 delta functions. So in principle, that's easy. In fact, it gets a little messy because, okay, you can do 3 of the integrals right away. You integrate over 3 of the momenta and they're gone, and now you conserve momentum. But now the remaining delta function is a delta function in the energies, which are something like the square root of p plus m squared, p squared plus m squared stuff. So you have to use the, for a delta function of a function, you know, the formula, sum over the zeros, 1 over the magnitude of f prime at the zeros, absolute value times delta of x minus xi, sum over all the zeros. So if you haven't derived that formula, derive it. I know I've said that very same thing to you before. So one of these times I'm going to say that and you'll actually, oh, I should derive that and do it. But it's true. So what you've got is a bunch of energies here that are sort of messy functions. This thing is a sort of messy function of your momenta that you want to integrate over the magnitude of the momentum and leave the angles. So what you want is the differential cross section is some stuff times the d theta and d phi stuff. So the last integral you do is over the magnitude of the remaining momentum. So you either have to express energies in terms of that magnitude or that magnitude in terms of the energies. And I've done an example of that, and I've posed a problem where you can probably dodge actually going through it all again, but it wouldn't hurt if you wanted to. But I'll post that section in the notes as soon as I clean up this stuff on virtual particles and resonances. A virtual particle is just basically any internal line, but the that calculation is in the notes. So read that carefully. That said, back to the diagram. How do we write the matrix element for this thing? And what do we got? So we've got polarization vectors, E mu of lambda. Let's call this E mu of something besides lambda, no, sigma maybe. All right, we've got I gamma, I-E gamma mu. I think these are going to be half positive and half negative, i.e. I'm not sure of that because, you know, half these lines are positrons and half are electrons. So I figure we ought to have an equal set of signs here. Here we're going to have E conjugate. This had better be an alpha. These polarizations have to line up with the associated gammas, right? So this one's got to be a mu. This one's going to have to be an alpha, and let's call it lambda prime maybe. And this one is going to be an alpha beta sigma prime. And then for these guys, we have propagators. So let's call this P1 slash, well, let's see, what do we get? So it's plus M for a positron. So this would be for a positron. Then here we can, let's see. Somehow this should circulate like that. But it seems like they should also alternate. Yeah, this has to be an electron. So this needs to be a positron. So I guess that's going the other direction. And this has to be an electron because at the vertex, this has to pair create, right? This has to pair create. So you've got to have, they've got to alternate. So the propagator for positrons has a plus here, and for electrons has a minus. Is that right? And let's call these, yeah, P3. No, let's call this one P2 minus M, P3 plus M, P4 minus M. Is that right? The propagator for a positron,
right
is that plus or minus?
I'm looking it up.
Are they the same? It could be the same. It could just be
looks like it's the same.
okay. All right. Yeah.
Yeah, it's always negative. It looks like you just have to keep track of the
U's and V's are
Yeah.
really keep track of that. Yeah, and they don't come into the propagator, so we just need the propagators. So let's see. We follow the loop around. Let's see. I wonder if there's a way you can rotate this so that it looks like the positrons are going the right way. But I'm not. Yeah, those three do, but that doesn't. This should be like a closed loop, right?
Yeah, it seems like, aren't you? I might be confused. It seems like we have a sync on the vertexes. Is that?
Yeah,
something's
wrong. Momentum should circulate here. So
yeah,
yeah.
It needs to be conserved because doesn't the arrow is the direction of the particle's momentum, so the positron moves against the
go around, I think, right? Or do they? Let's see.
I thought isn't arrow momentum, and then the particle moves, like positrons move against their momentum in time, right? Time propagate opposite from what you just naively like.
Let's see if I did this the other way. Let's see. So suppose this one's going that way. Yeah, it seems like I would want these coming into a vertex and these going out of the vertex. That's exactly backwards. Let's have these come in, and those go out. So we have momentum flowing that way. These are not actually momentum flow. This is just a way of keeping track in most diagrams of the particle antiparticle character of the fermions. It is not necessarily the flow of momentum, but
Professor, I don't understand why you're making these vertices. Like, why are you doing these like sources and sinks? I don't get that.
Because it's the only way that I can get the positrons going back in time. So if I draw them this way, it's consistent for these to be the positrons, and those could be the electrons. In fact, I don't know that matters for this diagram. We're going to impose conservation of momentum at each vertex, and That's really all we have to do. So let's continue with this with a, all right, let's call this K1, K2, K3, K4. And now, so we have to have P2 equal to K1 minus P1 at this vertex. Here, we have to have P3 equal to K2. I don't know, which way does it go? Yeah, these are both in, so I think we need plus P2 is going to be P3. Up here, let's see, if we have P4 in, then let's see, P3 is going this way. So we have P3. Now let's make this K3, this P3 plus P4. And here, okay, that's we took going out. P1 we have coming in, so P1 is going to be the sum of those two. P4 plus K4. Maybe, I'm not sure I got that right, but we need conservation of momentum at each vertex. So, and the arrows are not necessarily in the direction of the momentum flow. Let's see, we could do this. Yeah, let me try this again, and let's assume a momentum flow like this. So I'm going to write them again, assuming that. So that makes this one coming in, and K2 is coming in. So we have K2 plus P2 needs to be what goes out here is P3. Then here, P3 comes in, and P4 goes out. So P3 has to give rise to K3 and P4. Now this is coming in, that's going out. So P4 has got to give rise to these two, K4 plus P1. And here, P1's coming in, K1's coming in, and they have to give rise to P2. So I don't know if those are the same thing we wrote before. But this gives a consistent momentum flow around this loop, which is going to be the final integral, right? We have one loop here, so there's going to be an integral over the amount of momentum flowing in that loop. That's not determined by the K's. Now, all right, so yeah, these are probably, well, may or may not be what I had before, but this at least assigns a consistent momentum around the loop. And let's see, what we can do is try to solve for some of these in terms of others. So we can do the algebra here. We've got let's see. We should be able to solve for all of the P's in terms of some unknown Q and the 4 Ks. Among all these, there's one missing constraint, so we can't solve for all of the P's. There will be one unknown Q going around the loop. Okay, but if we try to write the matrix element, let me, let's see. Yeah, let's just start with propagators. We've got I over P3 minus M. I'm just going to go around the loop and see what happens. Gamma alpha I over P4 minus M. Gamma beta I over P1 slash minus M. Gamma mu I over P2 slash minus M. And we're back to, well, I can come here, gamma nu. We're all the way around now. And then we have all the epsilons, epsilon lambda prime, epsilon sigma, epsilon sigma prime. And those are going to be summed on the corresponding alphas. So lambda prime goes on alpha. So we need alpha here. Maybe if I put these down, I can put the indices up on the news on these. So let's see, lambda was this one. That's got to be mu. Then sigma is mu, and sigma prime is beta. And then we're going to sum on sigma, sigma prime, lambda, lambda prime. Let's see, averaging over these two. So two polarizations each should be a quarter. And that's going to, let's see, so when we square this, we're going to have, say, a lambda alpha, lambda prime, and its conjugate. Sorry, these are conjugate going out already. But we take the conjugate of the whole thing, multiply it in. So there will be all right, we're doubling this, so we have 4 more space-time indices. And this will also be a lambda prime. So the sum on lambda prime is going to give a minus eta alpha prime, which is going to contract some pair of gamma matrices when we square the thing. But okay, the sobering thing here is that we've got 1, 2, 3, 4, 5, 6, 7, 8 gamma matrices, and we square it. We're going to have a trace of 16 gamma matrices. Now, we're going to have 4 etas. That's going to reduce pairs after a bit of manipulation. But this is a hairy problem. I think this is basically the right thing. We need to enforce these. So these various p's are going to be expressible in terms of one another and one unknown q. And we can do various rearrangements. Okay, so here's the problem. The free indices here. If we take the conjugate of this, then the order of these is going to be mu, alpha, beta, mu. The free gammas are going to have these indices. We're going to take the conjugates in the reverse order. So we'll have some, let's see, which way will it go? So what, mu prime, beta prime, alpha prime, nu prime. Is that right? So the epsilons, the question is which epsilon is going to contract. So supposing that, the lambda nu is going to be a nu prime still with lambda. So we're going to get an eta nu prime, eta mu prime, eta beta prime, eta alpha prime. Now I'm racing through this. You want to do this carefully, right? I'm not positive I'm getting this right, but I'm just trying to guess how much commuting of gamma matrices I'm going to have to do to use these to reduce half the gammas. So it doesn't look too bad. If we reverse all this, it looks like mu and mu prime are already going to be just one p apart, and we know how to reduce that. Okay, then beta prime, we're going to have 4 propagators between the beta and the beta prime. So, all right, that's getting pretty hairy. So I'm thinking we will have to do a lot of use of the anti-commutation relation on the gammas in order to make use of all the etas. I think that's probably pretty messy to do. Hey, try it, you know, write it carefully, see what it takes, you know. So, you know, at some point it's going to be, okay, you know, this is like too much. But okay, suppose we successfully use all the etas, right? That gets rid of all the free gammas, and what we have left are 8 propagators. So we still have 8 gammas, right? Now, we do have some p3 squareds, and those drop out, but you know, this p3 is nowhere near the other p3. So we would have to do a whole lot of commuting of those gammas in order to reduce those p's. So worst case, we've got, well, a trace of 8 gammas. How many terms? So we need 7 double factorial terms to take that trace. And that's 7 times 5 times 3 times 1, 7 times 15, 105 terms is a lot, right? Now, so go program your computer and, you know, teach it to take traces. And people have done that. So anyway, I feel, you know, confident that with a careful drawing and a little more thought, I think this matrix element could be right, actually. I'm a little bothered by the direction of flow here, and yet, you know, that's got to be right. If we assume, we could assume that Q flows around here and use that directly, we might be able to write this a little more efficiently. But in any case, I will wager that among these 4 equations, there's 1 redundancy, so you only can solve for 3 of the p's, and there's 1 free momentum to be determined. And I don't know if that diverges or not. Yeah, what's our rule say? We've got 1 loop, so that's 4. We've got 4 internal lines. So 2 times the number of internal lines is 8, 4 minus 8 is negative. So let's see, is that, let's see, so internal lines are 1 over p. So that this might converge. This might be just fine. Yeah, try it and see. Yeah, good question. So I think that's roughly how you do that.
All right, sounds good. I'll take another look at it. I was trying to figure out how to just even write it down. So that'll help us a lot. Thank you.
Yeah, well, you know, sometimes just write things and it'll occur to you, oh, wait a minute, I should have done this, not that. But I think we're pretty close here. That might be right. Okay, so take a look at the momentum integrals dealing with that delta function in the calculation of the decay rate and the scattering differential cross section. There's a fair amount of relativistic kinematics involved in that, so I would like you to get on top of that. I don't think I posted that yet, so I need to. I'll take one last look through these notes and then post those. Post this version of the book. We're coming up fast here on page 300. 294, 95, 96. Oh yeah. Page 297, not counting the appendices. That's, I can't believe I wrote all this. All right, okay, any other questions? You folks good? All right, it's good to see you. So next Monday, 2 o'clock, everybody good with that?
I won't be.
Your next week's your bad week, is that right? Or your good week?
For the next month, I'll be probably post recording watching. But
Okay,
we'll
so
see. I'll try to stay in the loop.
yeah, okay. So send emails. I've opened up the discussion. Have you guys tried the discussion?
Yeah.
We were asking about that yesterday.
Yeah,
Thank
I've
you.
accessed
I haven't
it. It's
yet.
on there. I don't see anything posted.
I put it on. I thought I had opened it up on the Canvas
Yeah,
site.
it's up on Canvas.
It's okay. So use that however that's supposed to be used. I don't know anything about it, but let me know if you need my help for it, and I'll get the book up pretty shortly. I will send out an email when I've posted it, since the notifications from Canvas don't necessarily seem to be on top of things. Did you all get my email yesterday? Just confirming this time for this meeting. Okay, so do watch your email and email me if you have questions on anything. So I'll see you next week. There's some exercises here. There's plenty for you to do. If you get bored, do roller scattering, or pick your own. Get good enough at reducing these matrix elements that you feel like you've really got it. Okay, see you next week.
Hey, Professor.
Oh yeah,
Can,
Alex.
can I offer a countervailing point of view on the photon?
On the width, on the photon scattering?
Yeah.
Yeah. What did I do wrong?
And I'm just in I'm in the notes too, just double checking on 253. So I'm thinking that the arrows measure the direction of momentum flow, and that's why they're conserved. The flow has to be. They're like I guess they're the Wilson lines or something of the momentum. But
yeah,
but and then once you pick a time space orientation, whether you're going against time or with time for your propagators would determine particle antiparticle, because it'd be momentum propagating with time, momentum against time.
Yeah.
So when I did mine, I got that the left side was momentum. Well, I picked the left propagator as the left up propagator as electron. So I had the left.
Here, let me draw it your way. Let me try it.
Yeah.
I don't feel that I necessarily got this right. So okay, so we've got
Me either.
like this and a box. Okay, so now tell me what you want.
Okay, so I don't know if this is good double check. I don't know if so what I did is I labeled all the externals as polarizations.
Yeah, that's right.
And I did it as I did out as prime indices on the polarization vector, so that the two outs had K1,
K2.
and then I added the interaction at each so okay, well then the next step I did is I decided to orient time up and space to the right. So I started in the bottom left. And then I moved forward in time. So I started with an electron propagator. So arrow went up. And then I followed the electron propagators around. Yep. So I drew that arrow, conserving momentum.
So you circulate those. Is that what you did?
Because momentum can't propagate into the photon vectors. It has to stay in the spinner. The spinner doesn't propagate, but the momentum can leak. The scalar momentum. And then I labeled all of so that would be an electron.
Yeah, see that
propagator. Because it's
now,
I put space to the right.
Because you well,
because that looks like a photon scattering off of an electron then.
Yeah. All right. Yeah, we could do that.
Okay,
right.
And then the other
you want these to be the positrons?
And that's the positron.
So that's the positron scattering?
Yeah, that's what I got.
And then these are annihilations and those are scatters. Yeah, that could be. Yeah,
I mean, I'm just, this is spit on for me too, so,
let's see.
Um,
Yeah, all
and then-
right.
and then I-
So then that does correspond to my momentum flow here. What I ultimately went with was, just thinking of momentum flow to write the conservation at the vertices.
yes.
I need to check on this because, one of the sources I was looking at, it was insisting that the arrows were not the momentum direction. Let's look into this a little more. I'm not certain. For a lot of problems, the arrows are a nice mnemonic, but they may be working against us here. But I feel certain that we should be able to talk about the momentum, the free momentum flow around this loop as an undetermined momentum. And, deal with the conservation of momentum that way. I hadn't thought of this as a scatter, but that works. So if two of these are annihilations or productions and two of these are scatters, that works. Yeah, I was thinking each thing had to be a pair production or an annihilation. And that's why I was trying it this way with alternating plus and minus.
And
but yeah, that's a consistent view.
Is there the other way that I was trying to quick double check yours was can you do like the CPT really quick and see that it's invariant under any two of them? So like if you took the one we did on the left, there's like a net arrows down and there's a net arrows to the left. So if you did, there's a net arrow to the bottom left. So if you did like a CT inversion, you'd get it, the arrow would move to the top right. So is that a double check if you have like floating, because we kind of have here like sinks and sources. Is that a check with a CPT invariant? Is even if you have sinks and sources that graph momentum is CP invariant or whatever? Or sorry, CT and CP PT invariant, pardon me.
Yeah,
PT
so what, let's see, I had this as an E plus, but yeah, I should interchange those two, right? In fact, maybe we should draw it this way.
Yeah, okay, yeah.
So we have our positron line going back, we have our electron line going forward, and we can do something like this. So then it really is, our time direction works better that way.
Oh, wait, that's so cool. Wait, is this like a,
Just skew it a little, right? Skew it this way. So bring this to the top and that to the bottom.
I mean, is this a generic trick? Like this looks like a Kruskal diagram almost. like is that?
It's not a Kruskal diagram.
Okay, like.
But well, unless it is, I mean, that would be weird, right? But this is not even a space-time diagram. This is a Feynman diagram. It's a picture of something that doesn't exist, but it's a little piece of something that we can actually measure.
CPT ADS? Like the small is a
CPT. That's different. Okay.
Or no, what am I saying? Yeah, CFT ADS.
CFT. Yeah, right. Yeah. That's CPT ADS.
CPT ADS. Wow.
You got a new conjecture, Alex.
Yeah.
So, I did want to talk to you because I said the class is at 2, but actually it's at 1/4 of.
1/4 of 2.
Yeah. Just for you.
Today?
No, always just for you.
Oh, okay. Okay.
So you'll be there with everybody else.
Yeah,
that's just me shaking my finger at you.
Sorry, I was trying to get a research result in today, so.
Isn't one always, right?
I know.
Yeah,
Right.
I know, you get embroiled in something and, nothing else exists. I get it.
I have a feeling things are going to get put on hold next week too.